So let's start taking those points and turning them into entities. And we'll start with, well, the basics, right? So on the notes, it is showing the fact that C of M only takes points, right? So we're going to take these x, y, z coordinates for each point. And actually, each point that the CMM takes, it does get an x, a y, and a z, but it also gets an n sub x, an n sub y, and n sub z. So it takes the normal vector based on the point. These first things come from the basically the x, y, z read heads, or the slide mechanisms. There's a little optical reading head on each of the x, y, and z axes, and whenever the point is selected, it basically records x, y, and z position. But these things come from the LVDTs in the probe, and it indicates which direction the probe was, which direction was the probe displaced based on which LVDTs were moved and in what direction. So it does have those. Mostly we're just going to deal with the x, y, z points, but we do generally get normal data too. So all these different things, lines, planes, circles, spheres that we can measure. Let's start off with planes, right? So how many points to make a plane? 3, right? So maybe we've got point 1, point 2, and point 3. And these should define a plane. But really a plane isn't a triangular area here. A plane is infinite. So I'm not going to just represent the plane this way. Really the plane is represented by two things. A point, which is the centroid, or the middle of all the points. So this would be like P0. And a unit normal here, n, which would point normal to that surface. So n would be, well, I can't draw it here, but pointing out from that surface. So calculating the centroid, not too difficult. It's just the average of those 3 points. So for the x, I would sum from I equals 1 to 3, or 1 to n points of all those x points divided by n. And then I would do the same summation for all the y points over n, and sum all the z points. Okay, so there's our centroid, or our middle point, regardless of how many points we have. Now the unit normal, n, can also be figured out from those 3 points. It's a little trickier, so let me do it on an example on the board here, and we can use either the dot product or the cross product to figure out that unit normal. All right, so let's do an example with 3 points. P1 is 391, P2 is 442, and P3 is 653. Okay, so these 3 points make up a triangle. The centroid, P0, if I average basically all the x, y, and z components, we get 4.333, 6, and 2. So there's our middle point. And the plane will be represented by that centroid as well as a unit normal vector, n. So coming up with n, there's a couple of different ways. So we could use the dot product. Here we've got P1, P2, and P3. Now we know that any 2 vectors, if they're perpendicular to each other or normal to each other, the dot product is 0. So if we took this vector P1 minus P2, and we dot product it with n, we should get 0. Similarly, if we took P2 minus P3 and dotted it with n, that should be equal to 0. Now really doing it with that third length would be redundant, but we do know that n, really this normal vector n, is a unit normal, so that length should be equal to 1. Really, these three equations, we can set them and solve for these three components, n sub x, n sub y, and n sub z. So those three components make up this unit normal vector, n. Now, those aren't exactly linear equations. It's not too hard to do, but you can solve those three equations for three unknowns. But it's actually a little easier if we just use the cross product. So let's think about the cross product here. Now, the cross product, remember the result of one vector crossing the other, the result is a normal vector that's normal to both of those. So that's exactly what we're looking for here. So let's take P1 minus P2, cross it with P2 minus P3. And that should give a vector normal to both of those vectors. Now, it's not a unit normal. We'll have to, when we're done, we'll have to scale it down and take scale it to a length of 1 by dividing each component by the magnitude. But let's go ahead and do it. So P1 minus P2. P1 minus P2, that's minus 1, 5, minus 1, crossed with P2 minus P3. So that's minus 2, minus 1, minus 1. And if we apply our cross product calculations, we essentially get a vector minus 6, 1, 11. And I'll let you confirm that by applying the xa's and b's and all the different calculations there. So that's our vector that is normal to both of those. Now, it's obviously not a unit normal vector, so what's the magnitude of that? Is the square root of 36 plus 1 plus 121, right? So that's the 158, I guess. So square root of 158. So I would take each of these terms and divide it by the square root of 158. And if I do that, I get minus 0.4773, 0.0796, and 0.8751. So there's our unit normal vector pointing exactly perpendicular to the plane we've defined. Plane is represented by the centroid and the unit normal, and that's all we need to represent that plane. I'll do one more calculation here with planes. And I'll rewrite our normal vector up here. All right, so there's our normal vector and our centroid. And suppose we want to find the distance from some point, call it P, like maybe it's at 2, 2, 8. I want to find the distance from that point to the plane. Now, it would normally be the perpendicular distance, right? So we would draw a perpendicular line from that plane up to the point, and that would be the distance from a point to a plane. So let's create a new vector, which is the vector from the centroid up to that point. So that's really P minus P0. Okay, now with that vector, let's move the normal vector over here, because the normal vector is perpendicular to the plane. Well, the distance from that point, or the vector, to the plane would be the length of that vector, P minus P0, times the cosine of the angle between the vector and the normal, right? That's this angle here, but if I redrew n, then that's the angle right there. So P minus P0 times cosine of the angle is the distance. So that's the dot product, right? It's the length of P minus P0, or the magnitude of P minus P0 times the magnitude of n times cosine of theta? Well, magnitude of n is just 1, right? So it's the length times cosine of theta. That should give us that distance right there, the perpendicular distance. So, well, that's easy enough. It's just a dot product. So I compute p minus p0. So here's our point 2 minus 4.33, 2 minus 6, and 8 minus 2, dotted with our n vector here, minus 0.4773, 0.0796, 0.8751. The result is a scalar quantity is 6.0459. That's it. That's the distance from this point to our plane represented by the centroid and the normal.